Sorry about that. I think we're okay. I was just making sure my poor computer gets confused moving to all these different setups with different cables. So just making sure everything looks good on the stream. All right, I think grades are mainly caught up, or at least I caught up on the online grading in here for the most part. Um, Behind on paper grading again, but I'll catch up by Wednesday. I don't think I'm too far behind. And yeah, I don't know if my open math is going to happen for the last chapter. I haven't thought about it deeply enough. Slash, I've obviously fallen behind, but yeah, I'll just keep doing what I can with that. I think I should be able to do my open math for this chapter. This chapter's more conducive to it, more mathy. And then it is chapter 8 in our open stacks textbook, or like I said, any basic gas laws chemistry textbook should suffice. And then lots of handouts today, so I do have some solubility rules that kind of related back to some of our previous chapters, and then the lab and homework this week. All right, so let's dive into lecture, unless there are questions about anything. And so we'll kind of recap quickly. And so in the beginning, okay, we said that there are 3 states of matter. Solid, liquid, gas. Oh, sorry, my Wacom isn't mapped properly. And so today we're going to be focusing on our gases. And so gas, if you remember, right, our gas has an undefined volume. So we'll say no fixed volume, no fixed shape, which I think you'll remember from kind of the beginning when we went over these properties. But now we're going to add some more math to it. And so we said, do you want to shut the door for us? Oh, you want to shut the door? Shut the door, shut the door. Thanks. And so gas is then a phase of matter where then our particles are moving around randomly and fast in their container. And so we're going to look at just our basic kinetic molecular theory. And so that's kind of making some assumptions about our gas. So this is basically for an ideal gas. And we'll kind of mention the minor discrepancies. And so part of this ideal gas is we assume that they move in straight lines, right? And they're not interacting. And then they collide with a container. And then we assume that we have perfectly elastic collisions. And again, this is all just our assumption here for our gas laws. And so basically what we're saying with this kind of ideal gas laws kinetic molecular theory is I'm going to put that we're ignoring our intermolecular forces. And so we'll kind of get back into this, but basically we're saying, okay, we're ignoring any sort of interaction between our molecules. Again, they're just moving in straight lines until they collide, right, just like a perfect billiard ball. And then we want to start thinking about, well, what is pressure? And so pressure arises from the force of all these little molecules, right, actually hitting the walls of our container or our balloon. And so then you want to start thinking about a balloon and how it really functions. And so you have your balloon and you fill it up with air. And so all those little molecules of air, right, are moving around, colliding. And so them colliding keeps our balloon inflated. And right, it has to keep it inflated against the atmospheric pressure. So you have to think about that as well, right? So there's still air surrounding it, kind of beating back down. And then you guys obviously know, well, eventually this balloon may leak, and then it will no longer, right, be able to create that same pressure against our atmospheric pressure, and then we see our poor balloon start shrinking. And so here is pressure, again, just defining what it is. We won't really go into it, but we would just want to think about the force over the area. So again, like more molecules striking a certain area, and again, kind of what happens if we change the size of our container. So then, again, gas pressure is the result of this constant movement of our gas molecules and their collisions, right, with the surface. And so then we slowly start to get into the little bit of math that we're going to see. And our pressure depends on a few factors. Some of these are like self-explanatory. So kind of the more gas particles in a given volume, then you're going to have more collisions, which leads to more pressure. And again, you guys have seen that. You fill up the air in your tire, you keep going, keep going. You're adding more molecules, right? More pressure. And then we'll also see how our volume can affect it, right? Especially if we change the volume. Could be like a piston would be most appropriate kind of analogy, right? Where you can actually compress the gas. And then we'll look at average speed, which basically relates to temperature. So we'll kind of look at kind of what the speed versus temperature distribution means. But essentially we can sum it up to, right, as we increase our temperature, that will increase our speed, which is also related to kinetic energy, which is then more collisions. So you can see, right, again, kind of where this is going. And then just re-emphasizing that we're not taking into account any other forces, that we're just kind of treating it as, again, the ideal gas law. And so according to our kinetic theory of gases, again, this is over-idealized. So right now we're assuming that our gas particles, again, have perfectly elastic collisions, so no energy exchange occurs either. So again, just bouncing against another particle or against a wall, elastic collisions, and then just comparing to what an inelastic collision would be. So that's where you have energy transferred to a surface. And just thinking about this goes into like car crumpling and like why they crumple, right? So you may know that about cars, where sometimes they're meant to kind of crush in certain places, right? So that that energy of the crash gets transferred somewhere else. But again, that's inelastic, and we're assuming elastic conditions for our ideal gas law. All right, so then we have to figure out, well, how do we discuss the pressure? And so we have several units of pressure. So we'll look at where they were derived from. And so this is a pretty common tool that's used to determine the pressure, or also just like manipulate gases, which we'll kind of talk about in this chapter. And so it's useful to use mercury, for instance, to kind of help pressurize or back your gas up. This is actually what I used a lot of mercury for in grad school. So I used a small amount of mercury for reactions, but my main mercury was just using it as a bubbler for nitrogen. And so why this is, it's because it's very dense. And so something that you could do is measure your pressure. And so what you have is you have this tube vacuumed out, and then you have a pool of mercury. And then again, thinking about all those collisions, right? So the air is literally beating down on your mercury vat here. And that beating down is going to drive it up a certain amount. And so that's what happens. And so the amount that it's driven up, or the height of this mercury column, again at atmosphere, is 760 millimeters or 29.92 inches. Again, that would just work for your conversion factor. So 2.54 inches, or I went the wrong way, 2.54 centimeters equals 1 inch. So if you had to make the conversion, you could. So right, inches to centimeters, centimeters to millimeters. But then this gives us our main units. So this is what we need to focus on. And again, I would like write this down, or I might just give you a conversion on the exam, but this is something that you'll be expected to do. And then we also have this unit of torr. And notice that torr is the same thing as millimeters of mercury. So that's pretty commonly used. So 760 torr, so that equals 1 ATM. And so we have all our conversions down here in this little handy table. So we have another one that you might hear is pascals. So that's 1 Newton over meter squared, or the kilopascal, or K Pascal. So that would be kilopascal, and that would be 101.325. So kPa. And then again, just kind of orient yourself for other units that you may be familiar with or have seen. So PSI, they use that like for cars for the most part. Typically I think a car is at like 33 PSI or so for your car tire roughly. And then we've looked at these. The other one that you may see, and this is like usually, I've noticed this if you're looking at like the local weather report, they use bars for some reason, and so 1.013 bar is equal to 1 ATM, which is a little confusing. All right, let's try a conversion. Let's do our tire pressure. So let's convert 33 PSI. Let's see it in both ATM and torr. All right, let's see how we did. So what's 33 PSI to ATM here? Have our conversion factor, right? That sounds good. Is that what other people got? So I'm just sketching it out to catch up. So I see some nods. So I think that looks good. Oh, let me just put my calculator on the right screen. And so that's what you said, right? 2.25? 45, okay. 2.245 ATM. Good. So not too bad, right? Just our dimensional analysis. Any questions on that one? All right, looks like we're good. And then we can take this to Tor, so I would probably just start with the ATM. And then again, new conversion factor, so 760 Tor is 1 ATM. So how many Tor do we get for this one? 1,700, so looks good. It's about 1,700 Tor. Questions about those? And so, like I said, you'll probably be expected to convert between these. You will find out that ATM is kind of our standard unit, so generally you want to end up in ATM, but like I said, we'll keep getting into the math and what we should use when. All right, so then we have our four basic properties of gases. And so we'll have, like I said, pressure, mainly an ATM, so that'll be our standard unit. Volume, again, will usually be in liters. We'll go over when you can be in any unit and when you have to be in liters. Temperature is the one that is always, always, always Kelvin. And so that's due to thermodynamic relevance. So we have to have a temperature that starts off at 0 and then goes positive. So we can't have negative temperatures. That would mess up our formulas. And then just a reminder that we add 273 to our temperature Celsius. And then we don't need to worry about the 0.15. And then amount will always be in moles, so that's pretty self-explanatory. And then so we'll get into these gas laws. So we'll start off, we'll kind of look at the simple gas laws, but then once we're done, we'll look at how to summarize it. Maybe you guys have already seen it before, you know, our gas laws, PV equals nRT, but we'll get there. And so what we'll find is these properties are interrelated, and so if you change one, it's going to change the others. And so like I said, we'll start off with our simple gas laws that describe our kind of typical pair relationships. And hopefully I don't test you over the naming. I don't believe I do. That's not my intention in this class. Other classes you may see kind of this trivia, but we'll go through kind of the main three laws here. And so we'll start off with Boyle's law. And so what they were doing is, again, playing with some mercury. So again, mercury is always used to back gases. Well, now they've kind of tried to shift away from mercury to spring-loaded stuff, but mercury again helps you build pressure since it's so dense, right? So that's how you can actually fill a flask. And so they were measuring the volume and samples of gases at different pressures. So they were using a little J. Young tube, and then you add mercury to increase the temperature. So similar to this piston here. And so then they observed an inverse relationship between our volume and pressure. So right, basically saying if 1 increases, then the other decreases, or vice versa. And so looking at this little diagram here, we have our volume, so it's 1 liter. We start off with 1 atm of pressure, and then increase our weight on our piston. So now our volume is cut in half to 0.5 liters, and then our pressure goes up by that same factor of 2. And then I'm not sure if people have seen this before. You probably have. Have you guys played with these like vet simulations? So they should be linked on the website. So I think I linked to this one, but they're pretty fun to kind of play around with if you never have. It's kind of a mixed bag. I don't know if these have like fallen off in popularity, because it used to be like everybody used these all the time. And so we can kind of see Boyle's law. So let's first crank it up. And so now we have our pressure established. And then we want to hold, so it says right what we want to hold constant. So we could pick nothing. We don't want to hold our volume constant. We're going to change that. But let's just hold temperature constant, right? We're just looking at our pressure versus volume relationship. And so now we can play with it. So again, I'm just kind of watching our pressure gauge. We're at about 17. And then I'm going to try to double it. I can only take it so far. But we can see, okay, I made it bigger. So now our pressure dropped. Let's see if I can reset it to 17 roughly. Wrong way. Okay, so now we're back at 17. Again with our volume. And okay, let's try to half it. And so now I'm going to roughly half it. I did a pretty good job eyeballing that since we're, again, doubling our pressure to 34. And so like I said, it should be linked on Blackboard, and you guys can play with it all day. And then we have our graph here. And so again, our volume is inversely proportional to pressure. And obviously decreasing the volume forces our molecules into a smaller space. And then why do we kind of have this relationship here? What happens at these extreme high pressures? So very small volume, and then what does that mean though too? Yeah, exactly. And so we do however we want to think about that is like either it's condensing to a liquid, to a solid, or like he was kind of implying, the physical size of our molecules starts to matter at some point. And so again, that's where we start to have a little bit of deviation from this ideal gas law where we're pretending, okay, well, there's no interactions. And we're basically also pretending that they don't occupy space in this ideal gas law. But again, at these extremes, like he was implying, right, we're going to start seeing our material condense to a liquid, maybe even a solid if we keep pushing it all the way. Thinking about like CO2, for instance, right? We know we can compress gases to a solid. And then eventually, yes, we have our physical limitation is reached. And so then we have the math part of that. So we have this pressure times volume relationship is constant. So we could rewrite this as our formula. So our initial pressure times our initial volume equals new pressure, new volume. And when we're just looking at this comparison here, our units don't matter. So I'll say units don't matter, but must be the same. So AKA, right, milliliter, milliliter. Torr is fine. right, etc. So in this case, units don't matter. They just have to match on both sides since we're just doing a comparison to a constant. And so let's look at some other examples of this, of our pressure volume. Is anybody a diver in here? Anybody do diving? Nice. You have any scary horror stories for us or anything? Well, that's probably a good thing. One year I had ex-military guy, so he had some stories about people diving and not doing protocol. But yeah, feel free to jump in if you want to add something. Didn't like a bunch of divers just die recently too? I think I like literally just read about some headline. I don't know what quite happened. Something they went too deep or I don't know. Well, that's yeah, I mean, there's another story. Be careful going into caves. But well, let's get into kind of why it's dangerous so that we're all on the same page. And then we can talk about why people die. And so kind of roughly for every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure. And so they say at about 20 meters, for instance, then you might already experience 3 atm of pressure. And so let's think about, again, why this causes difficulties. And so now this is saying, suppose that a diver holds his or her breath and rises to the surface quickly, right? Your outside pressure drops to 1 atm. And so, right, what would happen to your volume of air in your lungs? And, right, this is kind of assuming that you're not breathing out, which starts to go into, like, why they tell you all these things when you're a diver. And so they say, okay, well, if you didn't exhale, right, your pressure would decrease by a factor of 3, and your volume would expand by a factor of 3 then. And so that's why they say, okay, well, always exhale while rising. But they fail to talk about all the other things that happen, and so really the other dangers. So what happens to all those gases that are in your blood, though, as well? Exactly. So that's why you're supposed to go up quickly, right? So that you don't get the bends. And so that's from like both oxygen and nitrogen in your blood, right? So the same thing. So they were kind of being, I felt like they were being kind of extreme in the example, like that's not really realistic. But what happens is, like, again, you have to give your body time to get the blood or the gases out of your blood. So that's why you're supposed to rise slowly to give your body time to adjust, which that's how we got into horror stories of the military, of people that like did panic and did not give themselves enough time to rise. And I mean, I think it just led to minor things like busted blood vessels in their eyes or something. But you still don't want, I mean, like that's what happens. Obviously, like that could cause more damage depending on like what blood vessel bursts. Like I said, I don't think in that particular story any major damage was done, but and then that also gets into like, I don't know if you've ever looked into the sport of deep sea diving. Like those people are crazy, but a lot of them do suffer injuries from obviously like the ones that hold their breath, dive all the way down and come back up. You have to, yeah, those people are like crazy. And like I said, suffer injuries at the very least, like busted blood vessels in their eyes. But I mean, again, you can have like major brain damage or something could happen depending on where your blood vessel bursts. Oh my gosh. Yeah. I mean, that's like slightly horrifying. Did your ear like recover now? Wow. But yeah, I mean, all that pressure, like behind your eardrum, like, yeah, that's pretty fascinating. All right, so let's do the math then, now that we're all scared of diving. No. And so let's do this little hypothetical scenario. And so let's say that we're studying this woman. She has an initial lung volume of 2.75 liters, which is filled with air at atmospheric pressure of 1.02 atm. And so let's just say, and this is kind of how your lungs work, right? So your diaphragm works to expand and literally opens up your lung capacity. And let's say, what if we could just like freeze that moment before your air rushes in? So what would be the pressure in the lungs then? So see if you can do that, and we'll set up our formula. So P1V1 equals P2V2. And so let me know what you get. So we're already in our standard units of liters and ATM, but like I mentioned, it doesn't matter. Let's just make sure we pair our initial conditions. So 2.75 liters, 1 ATM, and so new volume, so 3.25 liters, solving for X. So that will be an ATM. And so do we get this number? So I see some nods around. And so just kind of sanity check yourself, right? Make sure that it makes sense. So yeah, right, that makes sense. So if we're increasing our lung volume, I expect my pressure to be lower. And then just also make sure that that makes sense physically. Like, okay, well, that makes sense, right? Your diaphragm lowers, essentially creating like a mini vacuum so that the air can rush in your lungs there. So good. So X equals about 0.863 ATM there. Questions about that one? All right, so let's look at our next one. So now we're looking at our volume versus temperature relationship. And so now we're assuming that we have a fixed amount of gas, so we're not adding any moles, right? So holding our moles constant. And then we also want to keep a constant pressure. And so it's saying, okay, in order to have a constant pressure, the same amount, then that means that as our temperature increases, that our volume should also increase. So it's saying that they have a direct relationship. So again, right, you're increasing one, we're holding pressure constant. So that's kind of the key too, is that we want to hold pressure constant. And so then we get this formula. So V1 over T1 is equal to V2 over T2. And then again, star, emphasize whatever you need to do. But our temperature must be in Kelvin because we cannot have negative temperatures. Volume could be in different units, right? That's okay here since we're just looking at a relationship, but we have to be in kelvins for temperature. And so then we can play with this again. Let me see. I'm just trying to reset it for a little bit. And so now I want to hold. Sorry? Oh, let's see. And then let's put a little bit of gas in. Oh. Okay, so we're at about 5 atm. And then let's hold our pressure constant. And then it says that we're going to change the volume. Or it will change the volume, basically. We'll change the temperature. And so, right, we can heat it up. And so notice, right, how it's expanding. Our volume's expanding to keep up with the temperature. So we could cool it back down. So again, holding that pressure constant, right, it's shrinking it. And then we could probably play with the opposite effect. So if we want to keep pressure constant, but now it's going to fluctuate the temperature. So if I decrease our volume, right, notice the temperature decreased to also hold that pressure constant. So same thing, now make it big again. And so it had to warm it up. So now we're at 419 Kelvin to keep, again, our pressure at 4.7 atm. So again, I highly encourage you to play with this. It's a good tool to help you see it all. And so again, we're kind of seeing all this, and it hopefully should make sense, right, too, from just kind of what you've seen in your world. So when we increase the temperature of our gas, then again our speed increases, which is related to kinetic energy. So again, we can kind of think about this formula. We don't really need it, but right, that's what we're implying. So a volume increases, so does our kinetic, not volume, velocity, excuse me. Velocity increases, so does our kinetic energy. And then again, our collisions, so our pressure. So more collisions. And then, right, we're seeing, again, to hold the pressure constant, our greater volume spreads our collisions out. So thinking about the pressure equals our force over the area, right? So if we're trying to now keep our pressure constant, if we increase the temperature, right, we increase our surface area. And so this is another one where, again, we have the issue that real gases do condense eventually. And so it follows this nice linear relationship here. And so they can be extrapolated back to our absolute zero temperature. But again, like you guys have pointed out and all kind of know, well, in the real world, our gases are going to start condensing either into liquids or solids. And so we can't just follow this all the way. All right, let's look at another. I might do this like mini demo on Wednesday. I was thinking about it. Maybe I'll see if I can get some liquid nitrogen. Then we can play with stuff. But let's look at this nice video. Oh, hang on. I don't know if we're gonna have sound externally. I'm not sure. Hopefully it's feeding sound. I just
First
realized
back along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air.
Give me a second. See if this works.
Pressure, and you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. I just want to give you a sense for how strong, how rugged these barrels are. Jay, if you could stabilize the barrel, I'm gonna take a sledgehammer and try to. If you relied on me to crush this barrel, we'd be here all day. Because that thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So let me flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now, water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up. Okay. So help me flip this up on our stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice, solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
All right. So it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how big the flame we're going to work with. See, there's a good sort of jet of steam shooting out, and we're going to try to capture that by putting the plug back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But
mute myself. That part's important, right? So now they're like capturing, and we're not adding moles to the system. So that's where it's a little slightly different from what we've been talking about. But now we can look at our Charles's law, right? So okay, we've heated up the water, we've trapped our number of moles. So now we'll see what happens.
The key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. I'm going to just spin it down. Okay, through. Well, the first thing we should hear are a couple of the ends of the drum popping in.
There we go.
A couple of the ends going in. There's the other end.
There we go.
Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum, and because that water vapor inside and that warm air inside has cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is amazing. Looks like a pop can or a soda can.
Looks like a pop can or a soda can, or if you've ever rinsed out plastic milk jugs, and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe, at-home way you can do it.
Sure, yeah, no one, you know, having that blowtorch,
blowtorch is
for the experts like you, exactly. Well, this is really neat. A real 55-gallon steel drum crushed like it's made of thin aluminum.
All right, so that's a fun one. And then I don't know if you guys have maybe seen this on a small scale. Like I said, I could probably do this one on Wednesday too, but have you done like where you heat up the soda can. So you can do the same thing with a soda can, essentially. You heat it up, right? Boil some water in there. Like I said, maybe we'll do it on Wednesday. But it's fun to do, like, for your siblings. So you get it all heated up, then you turn it upside down in of like an ice bath real quick, and it should just collapse there. So that's a nice one.
The same thing can happen with rail cars.
With what?
Rail cars, like
Oh.
the huge ones, if you unload them too fast while they're heated up and then seal them back up, they'll just collapse in themselves.
Oh, nice.
It's terrifying.
I haven't heard. Are there videos of? Okay, I'll have to look up some videos. But yeah, I mean that makes sense. It's just I hadn't thought. Well, that's a good one. So yeah, pro safety tips too there. But yeah, so we can do some like mini variations of this for Wednesday. I You can also, of course, take a balloon, so same sort of thing, right? You can put it in boiling water, and it should expand, and then put it in cool water, or I was hoping, like I said, to maybe get some liquid nitrogen for Wednesday, and then obviously the balloon will really shrink there. And then, like they mentioned in the videos, milk jugs, maybe you guys have kind of noticed that effect where you rinse out the milk jug with warm water, and if you seal it on your counter, right, it should kind of go in a little bit. All right, let's do our little math example before we take our 10-minute break here. And so I'll rewrite our formula. So again, it's just our V1 over T1 equals V2 over T2. We do want to be in Kelvin. So this is like the biggest mistake that people make is they forget to go in Kelvin. But otherwise, it should be straightforward. And so let's look at our problem. So we have a volume of 2.8 liters at an unknown temperature. And then we submerge it in ice water at 0 Celsius. So we have to convert that to Kelvin. Its volume decreases to 2.57 liters. So what's the initial temperature? So take a few minutes for that one. So I'm just sketching it out. And so now, right, we can cross multiply and solve. So 2.8 times, and then notice I already changed that to 273 for Kelvin, and then divided by 2.57, which should give us, did we get 297 Kelvin roughly for initial temperature? So 297 Kelvin, and then let's or subtract -2, 73, and so about 24 degrees Celsius there. Do we all get that? So it looks like we mainly got that. So again, I think the biggest issues are just remembering to convert to Kelvin and then keeping everything right. Initial conditions, second set of conditions. All right, let's go ahead and take our 10-minute break here. So we'll be back around 2. And like I said, we'll keep looking at our simple relationships, and then I think we should get to PV equals nRT as well. All right, do we all make it back from break? Any questions come up or anything? All right, so now we'll look at our last relationship. So this one is, again, pretty like self-explanatory. So now we're saying that volume and moles have a direct relationship, again, holding pressure and temperature constant. And so that makes sense. So, right, if you're putting more moles into something and you're trying to keep your pressure and your temperature constant, then you're obviously going to need a larger volume to maintain that. And so let's play with that again. So let's kind of, let's see. So now we want to hold our pressure constant. And so now let's look. And so, right, you can see it gets kind of out of control pretty quickly. But as I put more in, so we'll reset it. So put a little bit, hold. Oh, come on, I need some pressure. There we go. Hold pressure constant again. And so, right, so just one more time, holding pressure constant, and then adding more moles. And right, you see how the container gets larger. And so that's all we're saying. And then we'll get to this as well. And so what's also kind of convenient about these gas laws is we're going to assume that a equal volume of gas contains equal number of molecules, so our gas identity doesn't matter. This is essentially true. There are small deviations for real gases, but for our purposes it'll be the same. And so then we're given this relationship of our V1 over N1 equals V2 over N2, where again N is our moles, and volume doesn't matter as long as the units are the same. And so again, you have a nice graph of that linear relationship. And so our volume is directly proportional to our number of gas molecules. So again, right, we increase the number of gas molecules. That's going to give us more physical particles to physically hit the wall or whatever pool of mercury we're using. And so like we saw with that nice FET simulation, to keep our pressure constant, our volume must then increase. All right, so let's try our little math scenario. And so now we're studying a male athlete in a kinesiology research study. And so that has a lung volume of 6.15 liters during a deep inhalation, and says that his lungs contain 0.254 moles of air. And so let's just say during exhalation, the volume decreases to 2.55 liters. And so watch what the question's asking, but it's asking for how many moles of gas does the athlete exhale during the exhalation process, and then assume constant temperature and pressure. So see if you can figure that out. I'll rewrite the formula for y'all. So try that out for a few minutes. So let's see how we're doing. So I'll sketch it out. So 6.15 liters over our initial moles. All right, so then let's solve for x. So just cross multiplying. So times 2.54 divided by 6.15. All right, so then we should get this value for x, right? And then, however, it's asking for how many the athlete exhales. So this is how much remains. So about 0.105 moles remain. So in lung. And so let's do our subtraction to figure out how much was exhaled. So 0.254 minus 0.105. And so that means 0.149 moles of gas were exhaled. Did we, at least I'll get this number. I don't know if we had finished the subtraction. Okay, it looks like this is simple enough. All right, so we have all those separate gas laws. But I really like the ideal gas law. Plus the ideal gas law will help us kind of rederive all our simple gas laws. So all we need to remember or write down ultimately is PV equals nRT. And so now we have our ideal gas law. And so this combines all our simple gas law relationships into one law. And so when we're looking at it in this formula, this is where all the units do matter. So maybe we should start. So units matter here. But let's talk about like where these units come from, because these units are really based upon R for our ideal gas constant. And so how you get to 0.0821 is it is from being in liters, ATM, moles, and Kelvin. And so what I also mean by this is, so let's just say you plugged into your search engine gas constant. So if you weren't careful, you would pull up all these different gas constants, but they're all based upon the unit. So that's what I mean is like our gas constant is dependent upon our unit. And so we could find the one that we're doing. Here it is, right? Liters, ATM, Kelvin, moles. And so because, again, we're in these units, that's how we end up with 0.082. Well, 1 rounded, you can obviously see it keeps going. But that's why we picked that one, right? And so all these other ones are if you were in other units. So, right, that one's for torr, and that one's for, water, blah, blah, blah. We have the energy one, which now I don't remember if we've seen that one in here. Maybe not. I sometimes mix up my classes. But this would be for R value with energy. So kilograms meters squared over seconds squared, Kelvin moles. All right, so again, all that is just to say that it depends on our units, right? So if you were in another unit world, then you would select the appropriate gas constant. But for our purposes, right, we will be in liters, ATM, moles, Kelvin, and so that gives us this gas constant. And so then we want to kind of do, I'll call it a baby derivation. And so what they're telling us here, so right, we have PV equals nRT. But then we just went over, well, R is a constant. And so that means we could rewrite our formula to give us PV over NT equals R, since, again, that's a constant. And so now we could set this equal to another set of conditions. oops, which then gives us our kind of combined gas laws where we have P1 over V1 times N1 over T1 is equal to any other set of conditions of P2, V2 over N2, T2. Oh. And so this is super useful, this form. And so like my helpful hint is really we just need to know this form and then we can rederive this form, which then helps us, I don't remember if it's on, I feel like there's something on our homework which has like 3 variables, but you could even have 4 different variables, right? As long as you have this formula. And then what you start to see, so I'll just make sure everybody has this copied, is now we could rederive all the simple gas laws we did by holding the other ones constant. I'll just give everybody another minute or so to copy this down. This is really, like I said, the chapter summarized in these 2 formulas. That's all we need to know. But then what we're seeing and what this is telling us is, okay, well, we can take this relationship P1 B1 over N1 T1 equals P2 V2 over N2 T2 and rederive all our simple relationships, right? So we get back to Boyle's by holding moles and temperature constant. And so you could eliminate those same variables. So right then you get to Boyle's. So P1, sorry, let me rewrite it. But then with Boyle's, right, we're holding moles and temperature constant. So, okay, that gives you your P1 V1 equals P2 V2. Same thing with Charles, right? So we go back to Charles's law, and we said we were holding our not temperature. We held our constant pressure in moles. So, right, we could do that. So Charles, again, just kind of rederiving everything. Just so we can see. So P1 B1 over N1 T1. So then we said, okay, Charles, hold our moles constant, hold our pressure constant, right? And then that spits right back out Charles's law formula. Right, same thing with Avogadro. We hold pressure and temperature constant. And so we could write that one really quickly just so we see. Let's pick another color. So P1 V1 over N1 T1, right? Always starting with our same combined gas law. And then, okay, Avogadro, we hold pressure and temperature constant. And so that gives us our same relationship. So just kind of pause there for a second. And so that's super nice. So again, that's just telling us that this is essentially all that we need to know, and we can derive everything else based off of what's being held constant. And so you might see a problem with 3 different variables or 4 different variables, and that's where you want to start with this relationship. All right, so let's try our practice one. So I think we might need PV equals nRT for this one. And I'll give you R. And hopefully you guys can figure out the rest. If I need to scroll back up for the units, let me know. So remember, we're in ATM liters, moles, Kelvin. So see if you can try this out. So calculate the volume then occupied by 0.845 moles of nitrogen gas at 1.37 atm and 315 Kelvin. So let's see how this one's going. So this one, I feel like it was pretty easy just because we didn't have to do any conversions. So right, watch out. The future ones may not be as easy. So we were already in ATM. They already even gave it to us in Kelvin. And so let's just multiply one side and isolate our variable. And y'all can let me know what you get for the volume as I punch it in. So 15.95, that's what my calculator spits out. Do we all get that? So excellent. Here, consensus. So good. So x equals 15. Lost my calculator. 0.95 liters. Technically, probably want to just give it 3 sig figs, so that would round us to 16.0 liters. All right, good. Questions on this one? All right, so then this leads us to more of our kind of relationships that'll be helpful. And so now we have our standard conditions, so commonly referred to as STP. So you might see that like in a paper or something reference, like, okay, we're just at STP. And so STP for our gas laws is 1 ATM, 0 degrees Celsius, or 273 Kelvin, and 1 mole. And then this is the important part, because this will be helpful. And so this also goes back to what we said. So we said, okay, 1 mole of substance at STP is going to occupy 22.4 liters there. And so they do prove it to y'all. We could punch this in ourselves, but all they do, right, is solve for volume, punch in the standard conditions, and then we get 22.4 liters. And so there's lots of little tricks I'll say that we can do, so we'll probably practice one. And again, we're assuming that 1 mole is all the same. So we're not looking at the deviations in this one, but we're just assuming, so helium is 22.4 liters, right? Xenon is 22.4 liters. And then they would have different masses, right? So then they do have different densities. And so remember, density is mass over volume. So again, a volume is constant here, but different densities. And then we could do something. Let's do a tricky question, but maybe think about a trick to how to solve this one. And we'll say, what volume does, we'll do 1.02 times 10 to the 24 molecules of methane occupy. And how can you make this an easy trick? Kind of going back, hint, hint, to these kind of relationships. So I'll give you all a little bit to think about it, and then I'll go over the trick. Oh, and I should have added at STP, just to be clear. Or else you wouldn't know. So do we have an answer, or what's a trick? That sounds about right, just from the mental math in my head. So let's go through it. And so you might see a problem like this, and I was trying to hint at how to set it up. And so we have kind of these relationships. And so proportions are super helpful. So we could set up a proportion. So right, we just said, well, 1 mole is 22.4 liters, which is also 6.022 times 10 to the 23rd molecules. So that's the easiest way to do this one. So I would set up that relationship. So 6.022 times 10 to the 23rd is 22.4 liters, just jumping straight to our relationship. And then setting up our proportion. So now just putting molecules on top, right, matching volume on bottom. And so now we just cross multiply and solve again. And so I believe that's what you said. So about 37.9 liters. And so you might see some problems on your homework like this, and it could ask like for moles or some amount, but all these relationships are super useful. Of either 1 mole or this many molecules is 22.4 liters. So that will help you with these problems. Otherwise, right, you're going to like maybe panic, convert this to moles, and convert that to liters, which isn't wrong, just as more steps. So you would still get there. All right, so then we get into Dalton's law, which is just basically our partial pressure law. But I think it sounds more complicated than it is. And so again, we're assuming that the particles have negligible size and do not interact. And so that means they have the same average kinetic energy. And so all that means is we can sum up the partial pressures. So it doesn't matter, again, the identity. And so that leads us to this relationship. And so all it's saying is, okay, well, we can have our fraction of our mixture, and either we know the total pressure, and then we can figure out the amount, the partial pressure basically of each gas, or we can figure it out from the moles and comparing the total number of moles. So basically this would be mole fraction. And then again, getting the pressure from that. And so again, we're saying they're additive. The gases behave independently. And let's look at an example. So this is just the derivation proving that we can add up the moles of our gas no matter the identity. And so this is mole fraction, so this might be useful. And so all we want to find is the total number of moles of what we're interested in over our total number of gases. And then we can divide the component that we're interested in over the total mixture to get your mole fraction. And so now it's easier if we put some numbers to it. And so you probably are already aware that our air, the air we breathe, is a mixture. And so now, okay, let's look at this. And so we say, well, nitrogen has a 78% composition in air. Find its partial pressure. And so all we need to do is multiply it by the total pressure. And then, right, we're just assuming 1 atm. So in our ambient air, we would find that nitrogen is about 0.78 atm. So again, it's the majority. And then we can add up our other components to get to our total pressure. And if you remember, oxygen is about 21% there. So there it is, right? 0.21 atm. And then argon is about 1%. So that's how you get to 0.01 atm. And then obviously trace gases aren't included. So they get pretty small pretty fast. But those are our main components. So pretty simple there. And we won't do anything too crazy with it in here. All right, so now we'll start our intermolecular forces. So now we're kind of slightly shifting from gas laws now to our intermolecular forces, right? So first we were like, okay, let's ignore these. But now we want to look at intermolecular forces and, well, what it means. And so we want to look at our phase change between states. And so we see that we can, right, add energy. So I have energy in the form of heat. And we have our triangle symbol. We could also put plus energy. And so, right, we need energy to go from solid to liquid. Then we start giving those particles, right, enough energy to slide past one another. Then add even more energy. Then we have our gas form. We can also reverse that. And again, we saw some phase changes with your little wax and what happened when you cooled it. And we'll discuss those lab results. All right, so now let's look at, well, what are intermolecular forces? So we were ignoring them the whole time. And so again, I'm going to emphasize this inter. So kind of like your interstate highway, right? Interstate highway is between states. Just like your intermolecular forces are between molecules. So right there, they're what holds separate molecules together. And again, this is what gives us our states of matter. So whether something is a solid, liquid, gas. And so now let's look at these intermolecular forces. And so this goes back to our previous big idea. So, okay, we have already kind of said this, but we'll reemphasize it because, again, it's what's driving our intermolecular forces. But all attractive forces are electrostatic in nature. That means we have some formally positive N and formally negative N, right? We've seen that from our ionic compounds, so that's what holds them together. And then again, we're going to be looking at the strength of these attractions now and at least somewhat generalize the state of matter given the intermolecular forces. And so then at room temperature, we need somewhat moderate to strong attractive forces to get materials to be a solid or a liquid. And then we're slowly getting to this, but right, the stronger the attractive force is, the higher the boiling point will be. So that kind of makes sense, but again, we'll keep thinking about this idea. These attractive forces vary in strength, so we'll kind of see roughly how to organize and characterize them. And then the stronger the attractive forces, then the more they resist moving. So again, right, making it a solid potentially. And then like we've stated, so no material completely lacks particle motion. So like we said, right, absolute zero is our theoretical point where there's absolutely no particle motion. But otherwise, right, we still have vibrations. You still have your electron floating around. And again, we'll look at our trends in our intermolecular forces. So the stronger the attractions, the more energy it will take to separate them, again leading to that higher melting point, boiling point. And so boiling a liquid, again, requires adding enough energy to overcome our attractions. And then this is important, so that's why I keep kind of harping on this. So we're not breaking any bonds. So right, when we're boiling water, we're not breaking these bonds. We're just disrupting our intermolecular forces here, right? So this, well, later we'll define it as a hydrogen bond, but this is our intermolecular force. And so that's what we're disrupting, right? We're not breaking covalent bonds. So that would be an intramolecular force. So important to make the distinction. So I will say, right, that I have seen OChem students confuse the distinction. So that's fine, right? You're 100 level, so good. It's a good place to be, and you're learning this now. And so again, the higher the boiling point, the stronger the intermolecular forces. All right, so going back to the idea of our electrostatic forces. So again, we're answering why are they even attracted to each other? And so like we've seen, we need some sort of attractive forces. So we've seen cation to anion. And we'll look at some others then. So we'll look at our polar molecule and how that results in our permanent dipole and what that means for our intermolecular forces. And we'll look at our nonpolar molecules and see how they can have temporary dipoles. And then again, same big picture concepts apply, that we have a larger charge is obviously a stronger attraction, and then a longer distance, weaker attraction there. All right, so we'll start with our dispersion force. And so it's our weakest of our intermolecular forces. And so before we read the text, let's look at our picture here. So this picture is pretty nice. And so we're looking at our helium atom. And so let's just say we're envisioning our helium atoms. And what if we could just freeze them for a second and look at a snapshot? And what if it just so happens that in this case, right, our electrons are on one side of our molecule. And so this gives us a partial negative. This leaves this region empty of partial positive. And then this could also induce the same effect in its neighbor. So then we'll have, what if the electrons are also on one side in its neighbor? And so now we have this partial positive with this partial negative, and maybe this keeps going for a while. And right, so it's frozen. And so in that instant, right, they are attracted to each other. But then, of course, right, these electrons will keep moving. Maybe it could kind of happen again on the other side, but it's always instantaneous, right? It's always kind of fleeting, again, because your electrons are moving round and round and round. And so it's very weak. And so let's look at our text here. And so again, like we're seeing, we have these small fluctuations in our electron distribution. And so that can result in our temporary dipole. And so like we saw, right, this gives us a partial negative on one side with our electron density, a partial positive on the other, where there's a lack of electron density. And so this gives us our dispersion forces, or you may have heard them called London dispersion or van der Waal. So I'll put that up there. So this is London dispersion or van der Waal, so depending on your source. So 2 names or 3 names for the same thing. And so again, it's just from our temporary dipole is established and could induce a dipole in our surrounding ones, but then, right, it'll keep moving around, and that effect will either weaken or move around, right? And so important things to note is every molecule and atom has a dispersion force. It's just for other molecules, like once we get to polar and hydrogen bonding, those are so much stronger that we don't really take into account our dispersion forces. And so we only really compare our dispersion forces with our nonpolar molecules. And so maybe I'll add that so dominant for nonpolar. Right, so for our nonpolar molecules, they are mainly dictated by just the London dispersion forces. And so with that, we have some effects. And so basically, the bigger it is, then the stronger our dispersion force. And so now we're just comparing all our noble gases. So of course, our noble gases are all nonpolar. And so what we want to appreciate is as our electron cloud gets larger, right, our mass increases, And so that means our electron cloud is more polarizable. And so their boiling point then increases, right? So that's the effect that we care about. Let me zoom in just a hair. And so all we're comparing is our mass effect versus our boiling point. So right, helium, obviously the lightest, is about 4 Kelvin. Also shows you why it's been used in a, well, traditionally NMRs were filled with helium to get them like super, super cold for the magnet. Now modern NMRs usually just take nitrogen now, which is a huge cost savings since, well, are you guys aware that helium is like an endangered element? Or yeah, so some of you guys have heard of that. So that's because helium, most of the helium comes from the radioactive decay. And now I forgot which isotopes, but basically it's from helium is called an alpha particle decay. So now I forget which exact species of like thorium and uranium, but basically they decay radioactively and release helium. And then part of the problem with helium is once it goes, it goes. And so obviously it's less dense. And so it goes out and leaves our atmosphere. So that's why it's considered kind of endangered. And most of these gases are all got through like fractionating your fossil fuels, right? So that's also why fossil fuels are super important, because that's how you get out everything else. Okay, anyways, sorry. A little bit of a side. And so then, right, increasing molar mass, increasing boiling point, all the way to xenon, having the highest boiling point of 165 Kelvin, obviously still very low for our gas, makes sense, right? Again, dispersion forces only. And then the other thing that affects our boiling point is our physical shape. And so a good example is if we compare, so N-pentane is going to be our straight chain. So 1, 2, 3, 4, 5 carbons in a line, and kind of showing the, again, tetrahedral nature of each carbon. And if we compare that to neopentane, so looking at neopentane, exact same formula, 5 carbons. If we counted up the hydrogens, they would each have 12 hydrogens. But with our neopentane, it's more of a ball, right? It's a very small, compact. And so that means we have a small surface area for interaction versus this large one here. And you can kind of see, right, they even like stack pretty nicely. And so, right, what much more surface area. And so we can see that difference in our boiling points of 9 degrees Celsius versus 36. And so, right, just even think about what would that be like to work with? Like, that'd be pretty irritating, I would say, to work with neopentane. I've never worked with it personally, but right, with that boiling point, you'd have to keep it in the fridge or in the freezer, and then what, you take it out, you use it really quickly as it's boiling off, or maybe you'd have to add it as a gas. You'd have to get creative depending on what you're doing. Versus pentane, right, which you can use at room temperature. It's even pretty low boiling, so that might be advantageous. So just things to think about. That's always what a chemist is trying to think about too, is like, oh, what's the boiling point, right? What's its property? How am I going to add it? And then, as you might expect, the boiling point of your N-alkanes increases with our molar mass. So again, just showing the mass effect now of our straight chain alkanes. And then octane, so that's what your fuel is made out of, or some sort of mixture of hydrocarbons. So octane is like more cleaner burning, so you can add that too as like a fuel injector. Otherwise, fuel is different hydrocarbon mixture, so mainly around that length of hydrocarbons. And it does make the point, so if we were looking at branch chains, they would have a lower boiling point. We could even get into like gas blends. So in the summer, right, you want something with a slightly higher boiling point, obviously, so your gas doesn't evaporate away, versus in the wintertime, it's okay if you use a slightly lower boiling mixtures. And so that's what the fueling stations tend to kind of, right, change those blends. That's a little irritating. Isn't ethanol like worse for your car too? Yeah. Yeah, that's a little disappointing. No. But yeah. So fun tips for summer there. Yeah. Do people still burn like vegetable oil and stuff, by the way? I was, yeah, I was curious. I was curious if people still do that with their diesel trucks. Well, anyways, that might be a good stopping point. All right, so we'll leave off there with those pro tips about gasoline in the summer. Also makes it hard to store gasoline long term too if you're trying to prep for the apocalypse. Anyways, so we'll pick up on other intermolecular forces. So we'll look at our polar molecules and some surface tension. So I'll try to bring some demos for Wednesday. And then grab the lab if you didn't already. So I look forward to seeing you Wednesday. I don't think it should be too dangerous. But at least come with your closed-toed shoes. And then let me know if you have questions. I'll keep the stream running in case there are questions. Otherwise, ask me questions in person.